The Arctic is cold, isolated, and dangerously unpredictable. Temperatures can drop below 50 degrees Celsius, the sun disappears for months, and storms roll in with no warning. You're not dealing with open land here, you're building on ice, snow, and fragile permafrost that's frozen hundreds of meters deep. And yet, scientists from all over the world live and work here year-round. Right now, there are 77 active Arctic research stations, operated by 19 different countries. Some sit on remote islands, others float on drifting sea ice, and a few are perched on top of moving glaciers. Together, these stations form the world's most advanced frontline for studying climate change, ecosystems, weather patterns, and atmospheric chemistry. But before you can run an experiment in this world, you need to survive it, and that means building in one of the most extreme environments on Earth. So how do you even begin to design structures that can stand on ground that melts, shifts, and cracks beneath your feet? Building in the Arctic is like racing a clock that never stops ticking. The ground is frozen solid, but once you touch it, it can melt and collapse. This is permafrost. And when it thaws, it doesn't just shift, it swallows foundations, tilts buildings, and turns your worksite into a swamp. That's why engineers use thermosiphons, long metal tubes filled with fluid that draw heat out of the ground to keep the soil frozen. Others rely on pile foundations, steel supports driven deep into the ground to hold a station above unstable layers. But the ground is only part of the problem. Arctic weather destroys weak materials. Winds reach 120 kilometers per hour. Freezing fog can shut down planes. Snowdrifts block roads. Darkness stretches for months. Regular concrete won't work here. It freezes before it sets. So workers either mix it on site under heated tents or build with prefabricated modules brought in by plane, ship, or ice road. And yes, some stations can only be reached by roads made of ice. These ice roads stretch over frozen lakes and rivers, but they only last 60 days a year. Miss the window and you're stranded. Even airports shut down for weeks at a time when snow and fog roll in. Fuel needs to be stored on site. Electricity might depend on diesel generators, solar panels, or wind turbines. Everything has to be planned months ahead, and even then, Arctic weather does what it wants. You can't just build and walk away. You have to build smarter, stronger, and faster than the cold. And every bolt, pipe, and wall has to survive a world where nothing is easy. So let's take a look at the most extreme stations built in this frozen world. Who's building what, where, and how they're making it work. Ny-Ålesund, Svalbard, Norway. Let's start in Svalbard, with a town that once mined coal and now mines climate data. Ny-Ålesund sits at 78.9 degrees north on the western edge of Svalbard's Kongsfjorden. It's not the northernmost outpost in the world, but it is the northernmost year-round civilian research town and one of the most important Arctic climate science hubs on the planet. Originally built as a coal mining settlement in 1917, it now hosts scientists from over 10 countries. But transforming a 100-year-old mining village into a modern Arctic research base comes with serious engineering problems, especially when the ground underneath is frozen and crumbling. This is deep permafrost country, and permafrost isn't solid rock, it's frozen soil, gravel, and ice, sometimes extending 300 meters down. When it stays frozen, it's strong. But as the Arctic warms, Svalbard's permafrost is thawing faster than anyone predicted. Engineers have measured mean annual ground surface temperatures, MAGST in Ny-Ålesund, ranging between minus 3.1 degrees Celsius and 1.9 degrees Celsius in just the past 2 years. In some spots, the soil is already passing the freezing point, which means the ground is no longer stable. And that's where the real work begins. Ny-Ålesund has 29 protected buildings, 23 of them built between 1917 and 1920. These wooden structures weren't designed for shifting permafrost. Instead of demolishing them, engineers had to reinforce the foundations using steel piers drilled deep into the soil. But not all buildings are equal. Some have open crawl spaces for ventilation. These stay cooler and stabilize the ground below. Others are sealed off, trapping heat under the floor. These enclosed spaces actually warm the soil beneath and speed up thawing. The solution? Engineers now recommend retrofitting historical buildings with vented bases, air circulation fans, or even opening floor hatches during cold months to encourage freezing. In newer structures like labs and accommodation units, Elevated steel platforms with spaced wooden decks allow wind to circulate and snow to stay out. These platforms reduce insulation from deep snow, keeping the permafrost stable. But even then, snow plowing and wind redistribution around buildings can raise temperatures unexpectedly. In some zones where snow accumulates, the MAGST has gone well above freezing, triggering talc formation on frozen zones that spread beneath frozen layers. Modern labs in Ny-Ålesund use high-performance insulation, triple-paned windows, sealed doors, and smart ventilation systems. Some use heat recovery from exhaust vents to pre-warm incoming air, saving energy and keeping interiors at 18 to 20 degrees Celsius. Power comes primarily from diesel generators, but renewables are growing. Wind turbines and solar panels support low-demand systems, reducing emissions in what's officially a zero-emission zone for visitors. Cars are banned. Aircraft are limited. The goal is to protect long-term data collection, especially from instruments monitoring carbon dioxide, black carbon, and aerosols in the atmosphere. What makes Ny-Ålesund unique isn't just its old buildings or clean air. It's the sheer density of science here. The village hosts observatories, satellite monitoring systems, a geodetic reference point for Earth mapping, and multiple climate labs tracking everything from solar radiation to ocean salinity. But all of this sits on ground that's literally moving, melting, and cracking with every warm season. Preserving the buildings here means preserving the science, and with the Arctic warming 4 times faster than the global average, that mission gets harder every year. Summit Station, Greenland. But to see what it takes to survive above 3,000 meters, you have to leave the fjords behind and head straight into the heart of the Greenland ice sheet in the Summit Station. There are no roads, no nearby villages, just snow, sky, and a base sitting on more than 3,000 meters of ice that's constantly moving westward, about 1.6 meters per year. Temperatures here can drop to minus 54 degrees Celsius with wind chill. The air is so dry and cold that metal tools snap if left outside too long. This is where the US built one of the toughest, most isolated research bases on Earth, the Big House. Summit's main structure, nicknamed the Big House, is a 17 by 8 meter steel-framed building that looks like a shipping container on legs. But those legs are key. They're steel columns up to 254 millimeters wide, driven into the snowpack, holding the building 5 meters above the snow surface. That height hasn't always been the same. Since 1990, the Big House has been lifted 4 times, totaling 15 meters, because drifting snow buries it fast. The problem with lifting a building that many times is that you start to strain the frame. It racks, it twists, seams start to split. So engineers ran an infrared survey of the Big House to detect heat leaks and stress points. They found that insulation at the base and in wall joints was under strain. Cables punched through the walls created tiny gaps where freezing air got in and warm air leaked out. One kitchen vent alone caused major heat loss, prompting a recommendation for a heat exchanger. Inside, Summit runs on an oil furnace connected to a 1,500-liter hot water tank. This keeps outdoor spaces around 20 degrees Celsius, even when it's minus 45 degrees Celsius outside. But every drop of fuel is precious. It has to be flown in by LC-130 planes that land on a snow-packed skiway west of the base. So engineers sealed every pipe, door, and hatch they could. Quad-pane windows are now standard. Double panes don't cut it anymore. Every exhaust pipe, power cable, and vent is wrapped in insulation. The floor, walls, and roof are layered with structural isolated panels, SIPs, each up to 229 millimeters thick. These panels include high-density foam and oriented strand board, giving structure while keeping heat in. But even with that, moisture buildup inside the walls remains a challenge, especially around the laundry area, kitchen, and toilet. Summit staff run continuous indoor temperature and humidity sensors to catch problem spots early. But it's not just snow and ice that threaten Summit, it's motion. The ice sheet underneath flows west, dragging the station with it. That means any rigid connection, pipes, data lines, even building frames can bend or snap over time. So Summit structures are designed to shift and settle gradually without cracking. Expansion joints and stress relief panels allow buildings to flex slightly. Even the bathrooms matter. Waste is sealed in tanks to prevent leaks into the ice. Fresh water is melted from clean snow, then stored in heated tanks. Nothing is left to chance. Not when resupply flights depend on clear weather and temperatures above minus 46 degrees Celsius. Summit Station supports world-class science. It's where ice cores have revealed 800,000 years of climate history. It's where scientists track greenhouse gases in real time, and it's where the tiniest mistake, like an unsealed hatch or a cracked duct, can mean losing precious heat, fuel, or data. Alert Station, Nunavut, Canada. But while Summit floats on ice, Canada's next outpost is anchored in raw frozen rock, closer to the North Pole than any other inhabited place on Earth. Sitting at just 817 kilometers from the North Pole, Alert Station faces temperatures that drop below -40 degrees Celsius, months of darkness, and howling winds that rip across frozen rock and ice. And yet, right here, Canada runs a fully operational military and scientific station. Keeping it running is an engineering war of endurance. The biggest enemy in Alert is the ground itself. This station is built on ice-rich permafrost that's incredibly sensitive to heat. If the soil thaws, buildings tilt, roads crack, pipes rupture. To deal with this, engineers elevate most structures off the ground to allow cold air to circulate beneath. This passive cooling slows permafrost melt. They also use thermosiphons, buried heat pipes that suck warmth out of the soil during winter. And since excavation disturbs the frozen layer, crews avoid trenching where possible. Every disturbance brings risk. Then there's drainage. Melting snow and trapped water can eat away at permafrost fast, so engineers build interceptor ditches and use insulation to redirect runoff far from the station's foundations. Under critical structures like fuel tanks or communication towers, you'll find reinforced gravel pads and ventilated layers that act like shields against thawing. Getting materials to Alert is another battle. There's no road here. Every piece of equipment, every drop of fuel comes in by air or icebreaker. That makes precision planning vital. Even culverts, those simple underground pipes for water, require extra reinforcement and insulation, or they risk turning nearby ground into swampy sinkholes. To top it off, workers have to battle frost heave, when frozen ground pushes upwards as moisture freezes and expands. So they test soil properties before building, drill monitoring wells, and constantly track ground movement using GPS and remote sensing. If something shifts, crews respond fast. Because one cracked foundation here means weeks of emergency repairs with no backup in sight. Living here isn't just hard, it's a daily balance between technology and nature, and the cost of a mistake, frozen infrastructure, cracked walls, or an entire building sliding out of alignment. Borneo Ice Camp, Arctic Ocean, Russia. But while Alert is anchored to solid permafrost, one Arctic station is built on something far more unstable. Ice that drifts, fractures, and vanishes beneath your feet. Borneo Ice Camp isn't built on land at all. It's set up each year on drifting sea ice near the North Pole. That means the entire base floats, moves, and changes shape under your feet. It's a station with no fixed location, and building it is a race against time. The ice here is usually about 1.3 to 2 meters thick, but it's far from uniform. Beneath the surface, ice ridges form as massive slabs crush together, piling up into walls of frozen chaos. To even find a stable spot for camp, Russian engineers drill deep using thermal drills like the ETI-3M2. These machines melt through the ice, recording how fast they move to detect voids, hard layers, and soft slush. It's the only way to know what's solid and what could collapse. Each year, the camp is assembled from scratch. Crews fly in prefabricated modules and drop them onto the ice. These modules are lightweight but insulated, designed to resist winds of 50 kilometers per hour and temperatures as low as -30 degrees Celsius. But even the best materials won't help if the ice starts to break. So the biggest challenge at Borneo is time. Once set up, the ice begins to drift fast. In 2013, the camp moved over 129 kilometers in just 2 weeks, with speeds peaking at 20.7 kilometers per day. Engineers monitor cracks, pressure ridges, and stress fractures constantly. If things go bad, they evacuate and rebuild somewhere else. The real wild card is the ice ridge beneath the camp. In 2013, a thermodrill profile revealed a consolidated keel reaching 5.8 meters deep. The sail, what rises above the water, stood 4.7 meters tall. But inside, a bizarre mix of snow, brine pockets, air bubbles, and porous ice. That means loads are uneven, temperatures vary wildly, and parts of the base are always at risk of collapse. The structures have to be light, mobile, and quick to disassemble. Yet, they also need warmth, power, and protection. Crews rely on diesel generators, portable fuel tanks, and heaters to keep equipment and people alive. Even one equipment failure can cause deadly cold exposure within minutes. When spring hits, the race to finish data collection intensifies. Cracks widen, ice thins, and the window to leave safely gets smaller every day. This is a camp where the ground isn't ground at all. It's melting, moving, and waiting to shatter. Zackenberg Station, Greenland. But not all Arctic research is this mobile. Some stations are built to last, perched between mountains and glaciers, where every supply flight is a precision landing and the ground is frozen for centuries. If you fly to the middle of nowhere in northeast Greenland, about 450 meters of flat gravel might be the only thing saving you from being stranded. That's the runway at Zackenberg Research Station, one of the most advanced high Arctic facilities in the world. It operates only in summer, but every moment is packed with data, coordination, and cold. The station sits at 74.5 degrees north, in the valley of Zackenbergdalen, right on the edge of the Greenland National Park. It's surrounded by mountains that climb over 1,400 meters, with glaciers, frozen lakes, and fjords cutting through the region. Underneath all of this lies deep, continuous permafrost. In most years, the active layer, the surface that actually thaws, reaches only 40 to 70 centimeters. Below that, it stays frozen solid down to 300 meters. Engineers had to work with the Danish Polar Center to create structures that wouldn't disturb this delicate layer. The main station includes 6 wooden buildings covering 275 square meters. These are fitted with heating, plumbing, and 220-volt electricity. But what makes Zackenberg different is its modular approach. Larger workshops and dormitories are built inside insulated tents called weather haven shelters. These tents provide flexibility while keeping warmth in and frost out. A new accommodation house with a garage and generator room was added in 2006 to support increased research. Everything needed to operate this station arrives by short takeoff and landing, STOL aircraft from Iceland. These planes land just 100 meters from the station, bringing in people, food, fuel, and equipment. There's no road access here. Heavy machinery is kept minimal, mostly rubber boats and a single ATV to minimize environmental damage. Waste systems are carefully controlled. Biodegradable waste goes into the river. Combustibles like paper are burned on site, while all solid and chemical waste is flown out, because even garbage in this place is considered too valuable to leave behind. Every summer, up to 1,450 person days are spent here. That means researchers, technicians, and logisticians cycle in and out, staying in tents, bunkhouses, or just working long days in the field. Most research happens within 1 kilometer of the main station, inside Zone 1A. There's also a low-impact zone, 1B, and a goose protection area, 1C, where access is nearly zero between June and August. Data collection is brutal here. Lakes are covered in 1.5 meters of ice until July. Snow lingers in valleys until mid-June. Temperatures swing fast, and storms can shut everything down. But because of this isolation, the region gives scientists a pristine look at Arctic ecosystems, from algae and thaw ponds to shifts in soil carbon and wildlife patterns. Abisko Scientific Research Station, Sweden. But you don't always need a plane or an ice runway to reach Arctic science. Some stations, like the one in Sweden, offer a rare thing in the north: access by train. Not all Arctic science happens in the deep wilderness. Just 195 kilometers inside the Arctic Circle, Abisko Scientific Research Station operates in a uniquely accessible location. Unlike other stations that require planes and weeks of planning, you can reach Abisko by train. This Swedish station, located on the edge of Torntrask Lake, is a permanent year-round facility run by the Swedish Polar Research Secretariat. The cold here is less severe than in Greenland, but the ground still holds permafrost, and the snow season lasts up to 200 days. What makes Abisko exceptional is its focus on long-term monitoring. Its first buildings were erected back in 1913. Since then, the site has grown into a full scientific village with research huts, greenhouses, labs, and dormitories, totaling over 4,000 square meters of infrastructure. Power, heating, and clean water are available all year, which allows for ongoing climate experiments even through the darkest winters. The station uses a network of soil sensors and above-ground instruments to study changes in vegetation, air quality, and permafrost depth. In winter, snowpack data is gathered daily using snow coring and satellite calibration. In summer, scientists monitor insect cycles, bird migration, and plant blooming. Engineers here face their own kind of problems. The ground is frozen, but not consistently stable. So, buildings are constructed on raised pilings or insulated concrete pads. Drainage systems are specially designed to prevent water buildup under the permafrost, which would cause thawing and sinking. One standout project is the Climate Impact Research Infrastructure, a platform of long-term experiments like warming tents and nutrient manipulation plots. These setups help model what the Arctic might look like in 50 or 100 years. All power for these projects comes from a central grid, and backup generators keep everything alive during power cuts, which are common in extreme storms. The location of Abisko also helps researchers test how ecosystems respond to less extreme but still Arctic conditions. This kind of controlled cold makes Abisko a bridge between the harsh polar world and the forests just south of it. Whether it's built on rock-solid permafrost or floating on seasonal ice, every Arctic research station is a combination of science and survival. These facilities are living machines, each one designed to stand firm in winds that rip off roofs and snow that never stops falling. And while the world keeps heating up, the Arctic is changing faster than anywhere else. These stations give you a front-row seat to the biggest environmental story on Earth. But which of these Arctic outposts impressed you the most? And what would it take for humanity to truly thrive in the coldest frontiers of Earth? Let us know in the comments and make sure to subscribe for more mega projects.